Okay, great. So, welcome everyone to the panel discussion, which is the last event of the day, and then you can go ahead for the afternoon in the beautiful Berkeley in the nice rainy weather. Today we have a very distinguished panel with us. We have Daniel Crowe from Atom Computing, Ken Brown from Duke, Dolev, who was our speaker earlier, from Harvard. We have Harry, also from Harvard, and we have Shruti from Yale. So, so we heard great talks by Dolev and Harry describing this amazing new development in experimental quantum computing, and it's a chance for us to explore this both as theorists or experimentalists to think about what this may lead to. So. In this panel, we could go one way. We could start with, on a positive note, talking about what all this great opportunity this experiment allows between theory and experiments. After that, we can talk a little bit about the obstacles, the challenges that were brought up multiple times during the talks, and then let's end on a positive note with what it holds for the future. So let's start with well, Harry and Dolev, you have spoken a lot, but maybe we could start with your view on what do you see as this technology bringing, the opportunity between theory and experiments, like correlated decoding, for example, or all the ways we need to think about quantum error-correcting codes given the constraints you have in the system. So what do you feel this might lead to?
So, okay, already doing these experiments, so doing an experiment, you always get desperate in one way or another to do something interesting. And so here, for example, we were desperate to find, interesting things to do with limited resources. And then I think have had new insights, if you know what I'm saying, both in terms of cheaper ways of doing certain algorithms or kind of better ways of doing decoding. So that I think that was true with this experiment. It's true in any experiment you ever do. And I think as we kind of go toward building larger devices, this will always be true. At least for the near term, I think as we kind of do more and more of these experiments, we'll only learn more. So I think we already kind of experienced that a bit. And I'm very excited about if we can make these medium scale error corrected devices, because maybe there's people here who've thought about this problem much more than I have, but I'm quite confident that however we do algorithms at that scale, we don't yet know what that looks like. So then kind of how do we approach that and how do we kind of come up with clever ways? I think that's very exciting to me personally.
Yeah, I think I mostly second what Dolev had. But I think what in kind of my experience was also interesting from some of these projects is you really get a much more functional view of how a lot of error correction works. Maybe I'll just give a small example from late at night when we were in the lab. We realized that for the 3D codes, you need to do the gauge fixing. And initially, we hadn't really thought about that. But then you kind of come with this very functional view of these very interesting error correction kind of ideas and observations. And I think it will be interesting to also see in the other direction, kind of motivated by these types of things, maybe some of these viewpoints actually can also inspire new theory developments as well. And we've already seen that a little bit with kind of some of these correlated decoding questions. I think this has also motivated people in the field to think about A32 codes, again, think about generalizations of them. So I think it's hopefully kind of a cross-fertilization in both directions.
Mm-hmm. So you could just continue down the line. So.
I think this is a great set of experiments, right? I think, even if we forget the actual decoding, error correction or anything, just controlling so many qubits, I'm sure it's hard. And the way you were describing that you have to have those AODs really, really properly aligned. So I'm sure it must have taken a lot of patience to do that. So yeah, congratulations. I think again, to me as a theorist, I love challenges, and the experiment has opened up new challenges for us to think about. Measurements is one challenge, and I so a lot of my research is to think about when I have slow measurements and what can I do with it. Come up with different ways to do quantum error correction or quantum computing that maybe we haven't thought about because we haven't been given the challenge that your measurements are slow and things like that. So I think it's just opened up a lot of opportunities and challenges, and therefore given us a chance to be creative.
Maybe some slightly more practical, maybe this isn't the crowd for it, but I want to echo sort of one of the points that Harry made at the end of his talk, that sort of the space of possibilities, both now and on the horizon for neutral atoms is huge. And I think there's an enormous amount of work to be done in figuring out what set of tools and techniques you can put together to make the best possible neutral atom quantum computer.
I guess on the positive note on the interaction between theory and experiment, I've been trying actually since 2013 to get people to try to do things like Kovalov and Pryadko's code, because I think it's a beautiful example of how you can get much higher density encoding. To no success, zero success. But then when the paper by Qian and Pablo came out showing how to use a neutral atom system to use these hypergraph product codes, I feel like, well, it is true. Many experimentalists called me and said, Lucan is now doing LDPC codes. We want to do LDPC codes. What's the right LDPC code for our device? Which I think has been good and fruitful. And like, that's like, I think to me, like a really positive impact in like pulling experimentalists towards doing quantum error correction.
Yeah.
Can we play with these systems? Like, if we want to build our own GC codes and try them out on the hardware systems, are any of them publicly available? Will they be?
So currently, I think the best route is to ask me very politely. I mean, so yeah, but so no, I mean, this is like a lab experiment. So it's not, there's no like cloud. I mean, so Harry also represents Quare, maybe he'll have a Quare thing to say. But this is like a Harvard lab experiment, in collaboration with other institutions. But yeah, but we're open to cool ideas. So yeah, I mean, also just even the process of programming what the atom motions look like is, I think, super interesting. And if there's a concrete experiment, either from you or from anyone else, I mean, we're super interested. I mean, the goal being to do an error-corrected algorithm that without the error correction, we could not have done that algorithm.
Yeah, maybe I will briefly comment a little bit from the Quora perspective. Yeah, that is definitely something that is on the horizon, and we're actively working towards that as well. So hopefully kind of soon you will also be able to do that. And I guess I should mention that there are neutral atom machines that are on the cloud right now. They are more geared towards analog simulation, because that was how the field kind of historically developed and where the technology first matured for providing cloud access for that. But hopefully in kind of the near future, there will also be other opportunities to more directly access it for these types of interesting things.
So yeah, you want to say some more?
I would also say, like,
Yes, yes.
atom computing, not currently cloud access, but though I am not the gatekeeper of machine time, I think if you have interesting ideas, I encourage you to reach out to us.
So, in these talks, we saw, there were several questions from the audience regarding the obstacles that there are currently in these systems. So maybe it'd be great from Daniel, Ken, and Shruti to hear, let's say, one obstacle that you think is the most crucial one, and let's see what Dolev and Harry have to say about that, or mutually, what do you think about that?
So like I think for me, as far as I understand, the obstacle is having very, very slow measurements. I know there are some opportunities to make it faster, or make it QND, and also like mid-circuit reloading of atoms. I think all of these go hand in hand, kind of similar challenges. Yeah, so I must say there are other platforms, other types of neutral atoms, like Hannes Pickler's, Burnyan, sorry, Hannes Burnyan's experiments in Chicago, as well as Jeff Thompson's experiments in Princeton. There are different kind of neutral atoms where I think Harness has definitely demonstrated mid-circuit reloading. I don't know what the time cost was or something. So I think there are opportunities there, but I'd love to hear more from them.
Should we respond or like
Yeah,
comment
yeah.
now,
Maybe,
or-
maybe just if you think.
Yeah. Well, no, yeah, I agree. I mean, no, I mean, so we haven't done mid-circuit reloading yet. Hannes has done this really nice with like a MOP reloading time of like 20 milliseconds or so. And then there's this really nice recent work from Atom Computing and Johannes Zeyer. I think that's an outstanding challenge. I share your assessment. Yeah, and then the speed. I don't know, do we want to talk about clock speed now? Maybe we can talk about clock speed later. Do you want to talk about clock speed? Or you go ahead. You go ahead.
I mean, I think it is still kind of an interesting open question for the field as to like, as we think about long run of these systems, as we go to kind of the billions of gates that people seem to need for a lot of things, how we actually bring all of those timescales down. And I think it will require kind of a concerted effort on all of the fronts. As we were saying, kind of there's a huge gap. We need breakthroughs on all of the ends, whether it's hardware breakthroughs, new schemes, new atoms, new kind of types of devices, as well as on the algorithmic front and error correction front as well. I think there's a lot of interesting directions to poke in.
Quick question. So is it possible to distinguish between just things that have not been done yet and real obstacles that you see? So where an obstacle, where a theoretical obstacle could be a no-go theorem, but I'm sure there are experimental obstacles where you say, well, such and such is impossible until you actually do it. So that's an obstacle, because, in terms of how you think about it, there's really an in principle obstacle until you break through it somehow. So are there such obstacles in any of the things that were mentioned?
So okay, for these medium scale devices, I think that, so we list these components of like 10,000 qubits, like 99.9% 2-qubit gate fidelity, mid-circuit, either non-destructive measurement, which is one option, which is really nice, or also mid-circuit reloading, has some combination of those two. And all of these, I am confident, very soon, people will be quite comfortable with different solutions too. And just having different solutions to different parts does not now make a fully functional quantum computer. So then putting that all together is also very challenging. But I am quite confident that those various ingredients are like very near on the horizon. So and these things are very, very rapidly developing. So, and there's, okay, those are the requirements, but then also, for example, there's Shruti and Jeff's erasure, which is also very promising. There's a different atomic species. There's multiple atomic species. So those are things we need, but then also these other things also probably will also work in various ways. And so what the kind of end up thing looks like, I think, that we'll have to see exactly, right? But yeah.
Can I ask a question since you're here? Is it very easy for you guys to like just jump to a different atom in your lab? Like you say you want to work with deuterium or some other atom, is it very easy to just use the same equipment you have, or you have to buy like completely new things, or like what are the difficulties involved in just changing the species?
So we would at that point, it's the opportunity cost would make it easier to just build a new lab. So, but these things, if you know what you're doing and you have a good team of people, this is not like it's not like we've been building this experiment for 10 years with some master plan. It's been like a random walk, and we're learning a lot as we go, and kind of we have diverse interests, right? So the I think in the near term we should be exploring many different species, or at least kind of the subset of the ones that currently seem very interesting. And we can't just spontaneously switch to ytterbium, but one can build a new machine that has ytterbium, for example. That's them.
So Daniel, I guess the platform that you think about is there's a difference between what Dolev and Harry do in terms of mobility of the atoms. So that's an obstacle, I guess. Yeah, do you want to listen on that?
So I think, let's see, I don't know exactly what I can and cannot say about what atom computing can do. I will say that in our we store our atom traps in our terbium device are cavity enhanced lattice sites, which are lower power, which is generally a bonus for us, because I think, well, I'm not an expert, that ytterbium requires a little more trapping power than, yeah. However, we have to load our atoms into those traps, and they come from a reservoir. So we also have tweezers with which we can rearrange atoms, and I think the cross-DoD architecture and or combinations of SLMs are all things that are feasible for us to do as well. So I think actually there are quite a lot of similarities, despite the underlying traps being slightly different.
I see. But there's still some difference in the sense that like being able to do all-to-all connectivity that Dolev and Harry think a lot about, that is a so what do you think of the platform they're thinking about? Or you cannot say too much at all.
I think all-to-all connectivity is a natural advantage of neutral atom platforms, and we are not ruling anything out.
I guess on my list of affiliations, I should always say that I'm a scientific advisor for IonQ, just as a note. I'm gonna, whatever, take the old man position here. So what's been interesting to me is, the original quantum computing experiments all involved NMR. The reason why was 2-qubit gates in NMR already existed because biochemists used them in a type of analysis called COSY. The downside with NMR is that you could not get enough spectral separation between the qubits. And in principle, you could do it, but in practice, you just kind of ran into this boundary. For ion traps, the original idea for a 2-qubit gate from Serac and Zoller, I think, was the last 2-qubit gate actually done. There was a really smart idea from a bunch of people, but the one we always say is Molmar Sorensen. And it led to this bloom of activity in ions, which allowed us to do a lot of stuff. And then we needed to think about how to transport and settle things around. And we had a solution in principle of surface electrode ion traps to just move things everywhere. But in practice, it took, it must have taken about a decade for the ability to shuttle and move ions to catch up with just doing experiments in a single chain of ions. I kind of feel the same way about superconducting qubits. So for example, superconducting qubits, they always used to argue about what's the best qubit. And then everybody switched over to transmons because they had a 2-qubit gate. They had good connectivity versus, good connectivity by these resonator strip lines. And then, these local capacitors. And it's interesting because then, from my perspective, then they start to run into the challenge of not being an atomic qubit and what are the challenges of fabrication. So again, with my neutral atom friends, I think the things which have been cool to see for me is originally everybody was optical lattices all the way. And then suddenly tweezers came along and it seems like almost everybody is oh yeah, tweezers, that's a great idea. And then I got a little bit excited about neutral atoms. I was like, okay, great, I've seen this shift. And then the second thing that got me more excited was these higher fidelity gates. But then when I try to look forward to think about what's the challenge, for me, it's still this atom loss. And I know in principle, you can reload these atom traps from whatever reservoirs, but in practice, I imagine that's gonna be a pretty tough challenge. So when you talk about doing 10,000 atoms and then probably, 10,000 squared gates, what kind of losses do you think you need to make that work?
So so currently we have roughly 0.1% loss per 2-qubit gate per atom. And so so you need to be able to replenish atoms at a rate that kind of corresponds to that. I think that this is going to be totally achievable. Yeah, we load atoms all the time, and we can load them pretty quickly. Now the challenge is to do that without disturbing the other atoms. And I'm not trying to trivialize these challenges. It'd be dangerous because then in the future, there'll be challenges, right? But it's not. You need the light to not hit the other atoms. It's not like there is. But otherwise, we're doing fundamentally the same thing. So I do share your concern, and I agree that it is the outstanding challenge. And I think people are working on it. And I think this is not We are not going to have this kind of conversation in 5 years. I'm certain. I think people are going to do that pretty quickly.
May I ask you, do you have a real-time control over which atom you lost or not?
Real-time, like knowledge of which atom was lost.
Right.
So we have techniques to deal with that. There's beautiful work from Shruti and Jeff kind of thinking about a different qubit where you can kind of directly detect erasure. We have different ways of dealing with loss, and we're working on it. Yeah.
So basically you are saying you cannot see whether you lost a particular qubit or not.
It depends on what exactly we do, and maybe the best I can say, I'm so sorry, is that we're working on it. Yeah, we're working on it. We want to deal with qubit loss.
But
Yeah.
ideally, do you expect that you at least will be able to look at it after sort of measurement cycle or something?
We will definitely be able to correct for atom loss. That's maybe, I'm so sorry. I don't know. That's probably right. Yeah,
If you do know the erasure position, you can sort of, by software, you can compensate for that pretty efficiently.
Right, no, I agree with you. There's many schemes to consider how to do it.
The other topics that were discussed, like power versus fidelity, and which Shruti brought up, and also there was a point about decoding and so on. So yeah, I guess you probably you want to
Sure. Yeah. Sorry if I'm talking too much, but at least the power one I can definitely do. So I mean so we have 99.5% fidelity gates right now. I think 3 nines is on the horizon. Yeah, I mean, at least theoretically, if you look at our atomic physics error model, we need to go 2 times further detuned and 3 times higher Rabi frequency. At that scale, the gate is roughly 100 nanoseconds, and then also we have to compensate for transients. But I mean, I think that that's very achievable as well, and there's no techniques to do that at that scale. So yeah, I think we should try. Yeah, we planned for 99.5, and then we got to 99.5, and then started doing other things.
So like if you had, so many number of qubits, and for that you had one laser of certain power, I think 100 watt or something to do the gate. So now if you have like thousands of these, you still need one laser, and so how will the power scale? Is it times 1,000? Or?
So, I mean, at the most extreme, you can continue to serialize in the way that we've done here. I don't think that that's necessary. Okay, maybe we're working on it. I don't know, but maybe I could say I do not want to buy a 100 kilowatt laser to build a large quantum computer. I think that there must be better ways.
And I guess maybe there was also a question about decoding. I think that is still an outstanding challenge, especially when we're really running things like heavily real time. We did demonstrate kind of mid-circuit measurements and feed-forward operations in this Harvard-led experiment, but then that was just like a very simple thing. I mean, it was like a color code decoder that we basically just like wrote a short C script by hand and then like outputs like one thing, super simple. But as we look forward, it is definitely something that we need to keep in mind about those challenges. And I think there's some interesting work also from people at this workshop thinking about some of the trade-offs as well, speed versus accuracy trade-offs. There's definitely a lot of room to also think about and play there. So I think it's definitely a question that the field still should continue to develop and try to address.
Sorry, can I ask a naive question? So let's say you have perfect measurements. Would you need continuous operation then?
Oh, like non-destructive measurements, like perfect non-destructive measurements.
So what does non-destructive mean?
Oh, so currently one thing that we're doing that I would describe as a bug and not fundamental. And again, this was like, okay, I get that. Yeah, I think I'm already at the point of just being honest. I mean, this setting up the mid-circuit readout is like, was like a few day endeavor, right? So we like did a few, we did the easiest possible thing. And so this easiest possible thing was a destructive readout. We non-destructively image the atoms all the time. And then we have to be like when we do kind of standard operation, but then you have to be a little bit more cautious about certain aspects. So
destructive means that you had an atom, and then when you measure it in 0 or 1, the atom is gone after that, and you can't mark
That's
it.
what we're right. Okay.
that's right. Yeah. So okay, thank you so much for the clarification. So even if it was perfectly non-destructive, which is certainly achievable from an atomic physics perspective, in my mind. And there's also, so moving for the most part causes no loss, but for the most part causes no heating. There's the transfers and so on. But I think what will be the fundamental thing is the 2-qubit gate, because that we don't know how to make perfect. Everything else in principle can be very, very good. And currently is limited by what I would describe as bugs. by like an overwhelmed team of people who are just trying to get it to work. And then but the 2-qubit gate, we will always have loss because there will always be some probability of leaving the population in the Rydberg state. And so we will always need some way to continuously reload the atoms.
So is it right for me to think of it like this, that there are these random error, random losses, but those are relatively infrequent?
Yeah, the way
As far as your syndrome measurements go, if you have two species and you can do your measurements, projected measurements on the one species, and now you don't necessarily lose any qubits there. So as far as that's concerned, that doesn't incur this big cost in terms of continuous operation. It's only for these occasional losses.
Yeah, from the 2-qubit gate.
That's the only place it comes from.
That is the fundamental one that I can never see going away. Because if we need to do, we do operations through the Rydberg state, this Rydberg atom, the population does not like hanging out there. And if you turn the tweezer on, this is a feature, the Rydberg atom flies away. So it doesn't stay around and make a correlated error, which would be catastrophic. But, now it's gone. So I don't think this will ever be zero.
So, sorry, just to clarify, so what I'm thinking of is not just feasible, but is it sort of what you think of as a practical way forward, or is it an idealized way forward?
Non-destructive readout?
Yes.
Yeah, I would do non-destructive readout in the future, but there's many different. But it's not necessarily. Yeah, sorry.
What is the time for non-destructive measurement? I thought it was like several tens of milliseconds.
Oh, so in our system, we can do it as fast as 1 millisecond if we're optimizing for that. And we typically do it like 5 milliseconds just because we're not speeding. But we've done it as fast as 1 millisecond with like greater than 3/9 fidelity, non-destructively. But the integrating it in. There's challenge. There's many different pros and cons. It's pretty wasteful to throw out all the atoms. I don't know, but maybe if you have such a high replenishment rate, maybe it doesn't matter. I think there's pros and cons.
I want to ask you about the scaling. So I understand right now your sample size is about 1 millimeter across.
Like 250 microns by 250 microns. Yeah.
Right. It's good enough for me. Right. So you would need to do several centimeters across, and then you will have the issues with field uniformity and all the field sort of, is there a way to go beyond sort of this size, like 10 millions, 100 millions?
Okay, sorry if I'm talking too much. But so field of view for sure. Field of view is, you can make a very big field of view. There's lithography objectives that have 6-inch field of views, right? In the
Semiconductor fabs.
Yeah, somehow you make this wafer, right, where you lithographize, at with hundreds of nanometer wavelengths, right? So field of view is not a problem in my mind. The problem is laser power. And I don't know. Do you guys want to take this one or I don't know.
One way to, I think, no.
Do you have anything you want to say, Harry? Or?
Yeah, I think, similarly to the 10,000 atoms, that seems really feasible. I think even beyond that is maybe 100,000 or so feels still very reasonable in sort of architectures that we're using with lattice traps and current field of views. But I think 100,000 atoms is probably not enough for the types of computations that people are used to thinking about with quantum computers. And so that is, I think, an open question and a challenge.
I don't know physics, but so you show all these transformations that are linear, and they're these affine. So can you do a shear or any nonlinear transformations or rotations of the plane as well?
Yeah, I think right now some of those are a little bit harder to do. For example, there aren't necessarily very good ways to do rotations with these tools right now. But again, this is something that the community is interested in developing, and I've actually given talks, and then my friends come and ask me if you were to start a new group doing integrated photonics, what should I do? and tell them, oh, do a rotation, that would be great, we'll use it. So I think it's something where right now the tools are somewhat limited in those types of things, but it's also totally imaginable that people are actively developing these tools to be able to do more general types of things. Yeah.
So going back to the 100,000 atoms being a challenge thing. So let's say the max size of a
100,000 being feasible.
sorry, yes. So you get to 100,000, let's say, and from there, the plan is presumably optical links. I saw kind of a throwaway bullet point on the slides, which was basically optical links. What are the biggest challenges there? Like, what are the current speeds? What are the theoretical speeds that you might be able to hit in terms of really scaling that beyond that level? I'm not necessarily only asking you, Daniel. So just the general.
I could answer. I mean, so people are totally working on. So atomic physicists love cavities. So I mean, they work with cavities all the time. I mean, including here at Berkeley. So I mean, these tools, now that people are very excited about these connections, people are working on it. And there's many different ways of generating this. And this is also, if you look at the numbers, I mean, is it theoretically possible? The answer is for sure yes. I mean, that's clear. So then it's again a question of, and probably in the coming years, people will also see that, oh, these tools also work. Now it's a question of, okay, do you really want to do it? Because that's also painful, right? So, I mean, but, yeah, definitely physically possible. But I mean, whether it's the easiest thing, I think is unclear.
So can you go back to this point about atom loss, which was kind of instigated by this discussion, by this question by Umesh. So I think Dolev at some point said that you can already deal with atom loss. So then is that still a fundamental challenge or not?
Well, I mean, yeah, it's one of our, but I mean, we're working on it. Yeah, we're just busy. Yeah.
Since this is an error correction, quantum error correction workshop, are there any theoretical problems you would like to see that people make progress on, or solve or put more effort into?
Maybe I can comment on that one, but others should also feel free to add. Definitely, I guess some of the questions that we already touched on, both in the talks and in terms of the theoretical side, and then eventually a lot of these theoretical things then motivate practical schemes. And then on the side of actually doing operations, I mean, pretty much all of the layers of the stack of actually building a quantum computer, we need breakthroughs on all of them. And I would say, for example, we want algorithms that are better suited both in the abstract model, but also now starting to think about how they match with the actual physical hardware. Going down on the QEC side, kind of codes with maybe better logical operations or kind of better code parameters. That's also always nice. I think all of these things are kind of things that would be of definite interest. And again, going back to what I said during my talk, I think it is something where if there are ways of getting 5x, 10x, even for now, not necessarily constraining yourself so much to the very specific modalities we have today, I think that would already be very inspiring for the whole community. And there are very many people who would then love to think about how we can take those maybe slightly more asymptotic results and bring them closer. And I guess next week, I think the Simons Colloquium will be Oded Regev's new algorithm. I mean, I think that's also a very inspiring example where the Shor's algorithm has been around for 30 years. And people have definitely looked at this problem quite extensively, but there's still new gems to find and new ways to get improvements.
Actually, quick thing. It's the week after next. Okay. But I had a quick question that occurred to me while you were talking about this. In the movement algorithm, where you were sorting and you were going doing this divide and conquer. So if you take into account that the movement time is probably proportional to the distance, wouldn't that say that that your time should be because of this geometric series, it should be the same as just one?
Yeah, and indeed, in terms of the total amount of time, it's a convergent geometric series. And so we actually do have that. I think it's 2 + 3 √2 or something. And yeah, indeed. And so I guess we were for us, we were counting the number of moves. And this is actually very closely related to also what Shruti brought up about kind of, okay, you're doing these transfers. So that's also a cost that we need to consider. But in terms of the actual time, it is indeed. Yeah.
I have a question. So again, maybe it's for very, very far future, but you drew in the picture that when sometime we'll have a quantum computer which performs with the error 10 to the minus 10. And again, additional to the field of view, I think the problem, if you keep all qubits in the same place, there is a lot of catastrophic events like cosmic rays, whatever, that can simultaneously destroy coherence of the device. So the question is, and if we don't want to go to some underground facility, deep dive something under the Harvard, we will need probably try to move things apart, right?
So I'll take it. So not clear. I mean, and I would say probably not. So we're not aware of any cosmic ray type events. You do have to be, correlated errors are the bane of error correction, right? And so, if, for example, the worst type of, okay, I said the Rydberg atom flies into the ether. What if it flies across the code in a perfect way, then like with one, in 10 to the 10? But we're not aware of things that happen like this. So one has to be concerned about it, but it's not clear that the spatial locality is even a clear problem.
Yeah, at 10 to the minus 3, yes. But at 10 to the minus 10, I'm pretty sure that at the level 10 to minus 10, there are a lot of events.
Well, but why does your computer work at 10 to the minus 14, right? It's like it's about technical limitations always.
Yeah, but because my computer consists of bits which have a lot of atoms, and you guys have individual atoms. They're much sensitive to this thing. So cosmic ray can destroy one bit, but in your case, cosmic ray can destroy a lot of bits. Or not even the cosmic ray. It can be like any radioactive decay, whatever events, like rare events, which happens in a chamber. You cannot So I'm curious that at level 10 to the minus 10, there will be a lot of events which can cause like big correlated error, and I'm curious that is there a solution for that? From my very naive point of view, it's the only way is to just move things apart so that there is not all eggs in one bucket. But I'm curious.
I think there definitely is kind of an experimental frontier to be probed there, and it is a question that does need to be addressed. And indeed, other systems have also probably earlier have started needing to worry about the same questions. For example, superconducting qubits, and they have like these both technical solutions as well as kind of distribution, as you said. So I think those are definitely possible solutions at that regime. But it is definitely something that experimentally will be important to probe. I guess maybe I'll just give the example that you gave recently. I guess people do atomic clocks with the same types of systems, and these do have, many digits of kind of accuracy. And so there is a sense maybe that you could hope that a lot of things could still work at the level of accuracy that you would want. But again, it's definitely something that you don't know until you actually do the experiment at that level, for sure.
So it's slightly close to the time, but okay, you're insisting, so go ahead.
Neutral atoms are 1,000 times slower than superconducting qubit operation speeds. Discuss.
Maybe we should hear other opinions as well.
I think, again, echoing one of Harry's points, like there need to be breakthroughs at sort of each level of the stack. Again, like sort of not wanting to say too much, like I think there are ideas about how all operations on neutral atom computers can be dramatically improved.
So this is not fundamental in your collective view.
So there's like the ytterbium atom that Jeff Thompson works with, they read out the slowest time scale is like 20 microseconds. So it's not 100 times slower than the 1,000 times slower than superconducting circuits. It's 10 times slower than superconducting circuits. So because the slowest time in superconducting circuits is the readout. It takes about a microsecond or 2 microseconds. So the factor of the difference is, smaller there. Yeah, and so it's still 10 times slower. That's annoying, but well, that's what we have. Um, yeah, but like even how to actually operate at that clock speed, I think it's still somewhat an open question of how to properly design your architecture so that it actually keeps working at that clock speed, because then you have to like really consider the details of the architecture. Like, are you going to do mid-circuit reloading, or are you going to then that will maybe decide the clock speed, or are you going to do kind of a resource state factory kind of a thing where you now trade off some of the time problems with having more number of resource states. So I think there's still a lot of optimization, a lot of room for creativity left.
Yeah. Then I just I want to jump off of Michael's question and then back to this coding question, actually, which is, Michael has this really nice paper where he looks at different clock speeds and different algorithm performances and what it would cost to do like really big things. To me, like the first takeaway from that paper is for like a lot of our dream algorithms to work, qubits have to become cheap. And once qubits become cheap, then we should always be able to trade off some parallelism for time. And we can even go to like, like you can literally take any space-time code and shrink the volume. So there's just like a thin layer of time and a ton of space up to some packing. Well, sorry, thinking about this old school braiding technology, right? Up to some packing of braids. But one of the things which slows us down is actually the fact that our fault-tolerant gates are not great. And I think if we could figure out how to get fault-tolerant gates on dense codes in a way that's efficient is good. And if we could go back to thinking about ways to, like basically efficient ways to tap into different parts of the Clifford hierarchy, I think there's a way that we can make all of these things quick again. And then once that happens, I become less worried about clock speed.
So, yes.
Quick, maybe superficial question. So these are cold atoms and they operate at the same energy levels as qubits, superconducting qubits, 6 gigahertz, right? And so now question is, because they're cold atoms, they're isolated from the environment, and so you don't really care about refrigerators. So you don't have in your lab, you don't have any fridges.
That's a true statement. Yeah.
Right now, but is there any like infrared? I don't know. You have to isolate. So what is about thermal environment?
So this magnetically insensitive clock qubit, its theoretical T1 is like,
Some 10 to the 15, something seconds.
it's like so crazy high. It's like this magnetic. There's like no dipole moment there, right? It's like superconducting qubit, same energy scale. Dipole is huge. So it's a completely different type of problem. There's no fridges in the lab. The atoms are microkelvin, but laser cold. The one place where blackbody does affect us is in our Rydberg state. So it's roughly half of our Rydberg decay error. Which is manageable. But
Okay, so I think we may have to move to the final part.
Oh, Umesh, do you want to? Okay.
A quick question. Maybe a quick question. I don't know. So is this an auspicious moment to start rethinking quantum architectures?
Yeah, I think so. I think, I think we, for a while, we got all trapped in this kind of 2D planar world. And then we put a ton of effort on 2D planar stuff, which has been good. And we made a lot of progress. And I think what's been nice actually in terms of the workshop is that because people are now more interested in these LDPC codes and we have to break out of 2D planarity, that starts to generate architectural requirements for the experimentalists to try to get to. But then at present, it's still unclear without actually going through all the details about how the gates work, whether in a computational standpoint, we can still beat the surface code. So I think work towards an architectural view that shows X amount of connectivity will give you this amount of gain in like computational time, say, I think would be very motivating for experimentalists to build towards that. And then I hope that, like one of my other hopes for the neutral atom experiments inspire theorists to realize that you can break out of these planes. There are ways to do broader connectivity.
I just wanted to add something to that. So there have been a lot of recent works on breaking this planar connectivity, right? Both in superconducting circuits and neutral atoms. My viewpoint is slightly bit more cautious that just because we think we can do it doesn't mean we should do it, because like there's a cost to it, right? So like there's atom loss at the moment whenever you load and offload things, and you are telling me that you may be able to control it, but well, I mean, it's tough, and it's my job as a theorist to make your life easier. So I think there's still room to think about when should we really move atoms? What is the cost of moving atoms? And design architectures a little bit more carefully. So we need a more thorough understanding, more thorough comparisons of different ways to do gates or error correction or whatever it may be, taking into account the costs of longer range connectivity. And only move atoms when it actually makes sense.
So sorry, then I should point out, so earlier in the week there was this discussion about like what is the cost of a long range gate, and what's crazy is no one knows because it's super platform dependent, super dependent on how you actually make that connection. Atomic physicists, like we love a cavity. So in a cavity, it doesn't really matter how far apart the atoms are as long as they're all sitting at the antinode of the cavity. They see effectively the same field as long as you can't tell how fast light is moving, right? And so in that case, there's like no distance penalty as an example, right? And so I think to Shruti's point, I agree, which is that as these technologies begin to give us the numbers we need to figure out what the actual long range cost is, then it'll just change how we evaluate what the right code is, what the right circuits are.
Yeah, so just coming back to the point, Shruti. So, I mean, as a theorist of a slightly different kind, to me, it's very attractive, this notion of moving atoms and doing transversal operations right away and working with logical qubits. This is fantastic. And I guess what you're saying is it's not clear that this scales or that this is the right way.
Yeah, I'm just taking a little bit more cautious view. I mean, I'm going to give a talk tomorrow, which involves atoms moving. So I think that I think that it's a promising thing. I'm just saying we have to be careful and not just assume everything is all. We know the optimal way forward.
So just to address the elephant in the room, there was a talk by Ben Bloom from Atom Computing a couple of months ago here at Berkeley. He sort of said, look, moving atoms, this is too costly. We wouldn't, so we'd rather do nearest neighbors or whatever because this won't scale. So, maybe we should discuss that thing a little bit.
Can I comment?
Yeah.
So
what would also have the atom?
Let me start with that.
I think his point about like long-term scalability is correct. That if you wanted to build something that required like 1 million or 10 million atoms for a computation that lasts a month or something like that, rearrangement might not be the way forward. But we have a lot to learn in the meantime.
To comment further, so I super echo what Shruti said, and I think it's absolutely correct to be super careful because it's not clear, right? And I mean, this is we're doing experiments and we're trying to get experiments working. And I mean, so I'm not on team atom movement. I'm on team build big quantum computer, right? So I mean, I think if we can in the near term, so I think long term being super careful, critical. I mean, because this is a long journey. In the near term, if we can make these medium scale error corrected devices, the types of conversations we're having are going to be very different. And we will never again talk about noisy random circuit sampling because it'll just be noiseless. I mean, the types of things we'll be talking about will just be different. So I think if we can get there, no matter what, that we will advance things, but also in the same time we have to be super careful and like think about all, I think it's both, we should be both, right? I mean, I think it's yeah. No?
Okay, so I guess the last part is really simple. We just give a big thanks to all the panelists for a very, very insightful discussion. And just enjoy the rest of the afternoon. Think about atom moving and not moving.
Yep.